Hello everyone. I am very honored to introduce my framework, GraphQL-state, an intelligent React state management framework. This framework consists of three parts. First, simple state management tool similar to Recoil. Second, GraphState management tool that is far smarter than Apollo Client and Relay. This is the core value of this framework. Third, HTTP optimization, an optimizer that can reduce the number of HTTP requests. In order to limit the time to 20 minutes, this video only focuses on the second part, GraphState. As for simple state and HTTP optimization, you can check related examples and documents. Content of this video: Scenario 1, refilter, both unoptimized and optimized. Scenario 2, resorting. Scenario 3, strategy choice. Scenario 4, bidirectional association. REST and GraphQL-client. Before understanding the intelligence of GraphState, we first give the core points. In the follow-up demonstration, we will discuss them through example demonstrations. The essence of UI state is that one main mutation causes n extra mutations. The more complex the UI, the larger the n. This framework allows developers to focus only on the main mutation, the other extra mutations are handled automatically. Let's get into the demo. Scenario 1a, refilter without user optimization. Simple state is not the content of our video to discuss, let's collapse it. Now enter the sub-demo GraphState, unoptimized. Here is a list of bookstores. There are two bookstores, O'Reilly and Manning. In order to show the follow-up demo, we first modify the name of Manning to Manning 1. This input box is used to filter the name of the bookstore. If we enter 1, after 1 second of loading, Manning 1 appears in the result because a 1-second delay is performed on the server to simulate the network delay. Similarly, if we enter 2, after 1 second of loading, an empty list appears. When we enter 1 again, no query is needed, and the result will be presented immediately. When we enter 2 again, the same effect. This means that the data is cached. Caching is the basic feature of all GraphQL-based state management frameworks. Of course, this framework is no exception. Now there are three query data in the cache: the query without parameters, the query with the parameter 1, and the query with the parameter 2. The framework also provides Chrome extension. We can open the developer tools, find the tab GraphQL-state, and then enter the sub-tab GraphState, and then we will see these three data. One thing needs to be emphasized. There are three data here, but the UI can only refer to one of them. In a normal project, the other two data may be released by the GC soon. However, in order to make it easier to go through our demonstration, the GC parameters of this example have been adjusted, and the other two data can survive in the cache for 1 minute, which is enough for us to calmly demonstrate the relevant functions. Now let's go back to the demo. In the Chrome extension, there is only one data left. The reason is that the discussion time we have exceeded 1 minute, which caused the other two data to be released by GC. The list at the bottom left of the page is the local data trigger log. These pink records indicate some data is released by the GC. Now let's quickly recache the data we need. Okay, all of them is recached. Now, let's change the name of Manning 1 to Manning 2. Obviously, the query with the parameter 1 has data before mutation but it has no data after mutation. If we enter 1, it will cause a refetching. After 1 second of loading, the new query result no longer has any data. The query with the parameter 2 has no data before mutation, but it has data after mutation. If we enter 2, it will also cause a refetching. After 1 second of loading, The query result contains data. In this example, the main mutation performed by the developer is to modify the name field of the bookstore object, and the extra mutations automatically performed by the framework are to evict those two parameterized query results from the cache. In this framework, evicting data from the cache will cause related queries to be refetched automatically. From the user's point of view, it is reflected in those two parameterized queries are automatically refetched. The filtering logic of this example is very simple, so it is easy to simulate it on the client side. The framework allows developer to participate in optimization, and developer only need to write very simple code to simulate this filtering logic. Once the developer completes this work, the function demonstrated in this example can be implemented without requerying, but directly modify the cache. Let's go back to the demo. First, let's restore the data. Okay, let's switch to the new example, GraphQL-state optimized. First, cache the data we need. The query with the parameter 1 has data, and the query with the parameter 2 has no data. Next, we perform the same operation, change the name of Manning1 to Manning2. If we enter 1, the query result has data before mutation, but no data after mutation. Yes, we cannot see any data now, but we did not see the reloading animation. At the bottom right of the page, we can see the HTTP request logs. In this list, the new record appears at the top. We can see that the last HTTP log is a mutation log, and there is no new query logs. If we enter 2, the query result has no data before mutation, but it has data after mutation. Yes, we saw the data, but we did not see the reload animation. The last HTTP log is still a mutation log, there is no new query logs. In this example, the mutation performed by the developer is to modify the name field of the bookstore object. And the extra mutations automatically performed by the framework is to delete the mutated object from the query result with the parameter 1, and insert it into the another query result with parameter 2. We have seen that the behavior of the program is correct, regardless of whether user participates in the optimization. However, if the developer optimizes, higher performance can be obtained. If developers are willing to participate in optimization, Chrome extension can provide guidance for developers. Let's go back to the example where developers are not involved in optimization, GraphQL-state unoptimized. Cache the data we need, open the Chrome extension, and find these 3 pieces of data. Now, modify the name of bookstore. Well, we see that in the Chrome extension, 2 data with parameters disappeared. If some queries in the UI try to reference these 2 pieces of data that have disappeared, it will cause refetching, as we demonstrated before. Let us switch to the subtab evict logs of the Chrome extension. You can see that there are 2 logs. Let us expand them. We can see their associated names and parameters, and why they were cleaned up. More importantly, the Chrome extension tells you that this scenario can be optimized, and what you should do if you are willing to optimize. Okay, let's talk about the second scenario, resorting. In daily development, we often encounter the requirement that the list needs to be sorted by some fields. Resorting has given strong support to this requirement. You can modify any fields of the object at will. If there are some lists sorted based on the modified fields, all these lists will be resorted automatically, no matter these lists are the results of the root object query, or the associated lists of other non-root objects. Let's go back to the demo. In order to better demonstrate resorting, let us enter the example, GraphQL optimized. This time, we click on the tab Page Book Management to enter the list of books. In this example, all lists are sorted in ascending order according to the name field of the object. Therefore, in the query result, we see that Learning GraphQL is ranked 3rd, and the smaller effective TypeScript is ranked first. Let us click on the tab page Bookstore Management to return to the list of bookstores again. As a parent object, the bookstore O'Reilly has an one-to-many association. Here, O'Reilly has 3 books. They are also sorted by the name field. Learning GraphQL is ranked second, and the smaller effective TypeScript is ranked first. Go back to Book List, edit Learning GraphQL, change it to Effective GraphQL. Okay, let's take a look at the sorting of the list after mutation. We found that Effective GraphQL ranked first. Entering the bookstore list again, in the one-to-many relationship of the parent to O'Reilly, Effective GraphQL also ranked first. In this example, the main mutation performed by the developer is to modify the name field of the book object. The extra mutations automatically performed by the framework are moving the mutated object to the forefront in the global query list, and moving the mutated object to the forefront in the one-to-many association list of its parent object. Let's talk about next scenario, strategy choice. Through the previous examples, we know that the framework automatically helps developers apply extra mutations. Sometimes it chooses to modify the cache directly, sometimes it chooses to evict cached data and cause related queries to be refetched. The first method is high performance, but cannot adapt to all situations. The second method requires HTTP communication, but is suitable for all situations. The framework will give priority to the first method. If it's impossible, it will choose the second method. This is called strategy choice. Next, let us use a very common problem in pagination query to illustrate this choice logic. First, click Author Management to enter the author list. Open the Chrome extension and enter its tab Evict Logs. Adjust the width of the Chrome extension so that it does not affect our presentation. Now, the UI presents 4 authors. There is a Load More button below, and 1 row left is displayed on the right. This is a forward-style pagination query. Now the total number of rows is 5, and 4 of them have been loaded. Let's take a look at all the data. Click the Load More button. After 1 second of loading, all 5 rows have been loaded. Okay, let's restore the data. Click the Refresh button to force a refetching. After refetching, it is restored to the state with only 4 loaded rows. This list is sorted by name. We can see that the first letters of the 4 loaded data are A, B, D, and E. Now, let's create a new author with the name C. Obviously, after mutating the server, the framework can directly modify the cache and insert the new author after B and before D. Yes, C was inserted in the desired position, but we cannot see any loading animation. Look at the HTTP request logs at the bottom right of the page. The last log is a mutation log. There are no new query logs. What about creating an author named X? X is larger than all the loaded rows, so it seems that it should be inserted at the end. However, the Has Next Page field of the current page result is true. That means there are more unloaded rows. The framework cannot conclude that X is less than all unloaded rows, so directly modifying the cache will not work, and the framework will be forced to refetch the query result. After 1 second of loading, we see that the list is refetched. In the HTTP request logs, we can see that the last log is a query log. Click the Load More button. After all the data has been loaded, X is ranked last. Let's restore the width of the Chrome extension. It recorded the state evicting, told the developer the reason, and clearly pointed out that this situation cannot be optimized. Let's talk about the next scenario, bidirectional association. Bidirectional association is a business-level cognition, so the schema of GraphQL has no bidirectional association. However, the framework allows developers to use very simple code in the configuration phase to bind 2 associations together to create a bidirectional association. For this examples of this framework. First, in Bookstore, there is an one-to-many association field Books. Second, in Book, there is a many-to-one association field Store. These two associations have been bound into a bidirectional association. Let's go back to the demo. The most suitable example for demonstrating bidirectional association is local data. Let's get into this example. Table in the upper area shows the list of bookstores, where each bookstore has a one-to-many association pointing to books. Here, O'Reilly has 3 books, and Manning has only 1 book. Table in the lower area shows the list of books, where each book has a many-to-one association that points to the bookstore. Here, except for GraphQL in action which belongs to Manning, the rest of the books belong to O'Reilly. In local data, the objects at both ends of the bidirectional association are cached and displayed in the same UI panel. Therefore, it is very convenient to use local data to demonstrate bidirectional association. Please note that this does not say that other examples do not have this feature. Let's modify the bookstore Manning. Now it only has 1 book. Let's append another book learning GraphQL into it. Finally, we save this mutation. Okay, let's take a look at the states after mutation. 1. Look at the bookstore Manning. Before the mutation, it had only 1 book, but now it has 2 books. This mutation is caused by our operation. 2. Look at the bookstore O'Reilly. Before the mutation, it had 3 books, but now it has only 2 books. This mutation is caused by the framework. The association between bookstores and books is one-to-many, not many-to-many. That means a book cannot be shared by multiple bookstores. Adding a book to a bookstore naturally means that the book must be deleted from another bookstore. 3. Look at the book learning GraphQL. Before the mutation, its store is O'Reilly, but now its store is Manning. This mutation is caused by the framework. In this example, the main mutation performed by the developer is to append the book learning GraphQL to the bookstore Manning. The extra mutations automatically performed by the framework are to delete the book learning GraphQL from the bookstore O'Reilly, and set the bookstore of the book learning GraphQL to Manning. How many extra mutations are there? Do you remember the sentence mentioned at the beginning of the video? What is the essence of UI state? One main mutation causes n extra mutations. The more complex the UI, the larger the n. In all the previous demonstrations, I only discuss extra mutations related to the topic at the time and ignore other extra mutations. In fact, the number of extra mutations is more than what was shown in the video before. Let's go back to the demo, and see how to view all the extra mutations. Enter the example GraphQL optimized, click the tag Book Management to view the book list, and open an editing dialog at will. In this dialog, we can see all the fields we can modify, the scalar field name, the many-to-one association field store and the many-to-many association field authors. Each field contains an embedded document, and you can expand it. These contents indicate what extra mutation will be performed if you modify this field in the main mutation under the current complexity of the UI. So far, all the example demonstrations have been completed. Let's talk about last topic, REST and GraphQL-client. The project name is GraphQL-state. Don't worry, it's GraphQL style, but not GraphQL only. It can map REST service to GraphQL service. Why is there such a design? Why the client should treat all services as GraphQL services? Because I also provide another framework called GraphQL-client, which is a GraphQL TypeScript DSL implementation. It can bring you the ultimate development experience. GraphQL-client is very simple. Let's look at a GIF animation. It automatically infers the type of the return data according to the strongly typed query request. Here are the addresses of these two projects. Thanks for watching.